order to define topology, we need a non-empty set. So here we are taking a non-empty set. First of all, we should understand that what is a non-empty set. The non-empty set means that the set which have at least one element, but this set can be contain more than one element. So to define a topology, we need a non-empty set. So here we are taking a non-empty set X. Let X be a non-empty set. Okay, since X is a non-empty set, and non-empty set means that it must contains at least one element. So what are the properties that will be hold on this set, okay, to define the topology? So X is a non-empty set, and from this non-empty set we will take a collection, and let we say that let tau be a collection. Let tau be the collection. And what type of collection? Tau be the collection. Okay, and okay, when we talk about collection, then collection means that there are number of which may more than one. Okay, more than one elements. Okay, let tau be the collection of subsets of X. Collections of subsets of X. Okay, so if it is a collection, then we say that tau is topology on X. Okay, tau is topology on X. Tau is topology on X if there are certain conditions. If those conditions are satisfied, then we say that tau is topology on X. Topology on X. If tau is topology on X, if the following axioms hold. If the following axiom hold. Okay, and what are those axioms? But remember over here that first we are talking about tau is the collection of subsets of X. The following axiom holds. A union of any number of members of tau. What we are talking about? Since tau is the collection of subsets of X, and in this collection the union of any members of any number of member of tau, any number of members of tau. Okay, the union of any number of members of tau belongs to tau. It's okay. Means when we take the unions of any number of members of tau, then that union should belongs to tau, and tau is the collection. Okay, now this is the first property for a topology, and the second property is, since in the first property we are talking about the union, and in the second property we will talk about the intersection of any member of intersection of intersection. So when we talk about intersection of finite, remember that here we are talking about intersection of finite members of tau, finite members of tau belongs to tau, it's okay. And the third property is it is just like phi and x. Phi means that empty set. Phi and x must belong to tau, the empty set phi and the set x. Phi and x must belong to tau. So when we look about these properties, okay, remember over here that first is there should be a non-empty set, and that non-empty set, from that non-empty set we will take a collection of subsets of x, and that collections of subsets of x is represented by tau, and there should be three properties that should be satisfied in tau. The first property is it is just like the union of any member of tau must belong to tau, and the second property is the intersection of finite member of tau must belong to tau, and third property is phi and x must belong to tau. If these properties are satisfied, then we say that tau is topology on x. Okay, yes, then if these properties are satisfied, then we say that tau is topology on x, and when we write it in this pair x comma tau, then we called it just like x comma tau. Okay, topological space x comma tau is a topological space. This is topological space. So after defining topological space, remember that the member of tau also called open sets. The members of tau also called open sets, and since the members of tau are called open sets, and if we represent it just like O is the open set, we want to write in this definition in mathematical form. So what is the mathematical definition of topology? It is very simple. Yes, we will define it just like our topology. Topological space, and when we talk about the topological space, then that means that we are talking about the pair. Okay, and the pair is x comma tau. A topological space, what pair is x comma tau? This pair is a topological space is a pair x comma tau. Yes, and you know x is a non-empty set. Of course, x is a non-empty set. X is a non-empty set, and we know that tau. What is tau? Tau is actually is a family. Okay, what type of family? Okay, family means that this is a collection, family of subsets of x. Okay, of x, such that by writing in mathematical form just like that, if the first is if O alpha. O alpha over here means that open sets. Open sets means that members of tau. Remember that members of tau are represented by O alpha, and here any number of members of tau. O alpha means that any number of members of tau, and alpha belong to I, okay, and this is contained in tau. This is contained in tau. Then by taking union, by definition of topology, when we will take the unions of any numbers of members of tau, O alpha, alpha belong to I means it may be infinite, okay. Their union must contained in tau. Their union must contained in tau. This is the mathematically. The first we define the theoretical definition of topology, and this is the way of mathematical definition of topology. And similarly, if I take OK, OK is finite members of tau. Finite members of tau where value of k is equal to 1 to n, okay, and we are taking it from the collection tau. Any, not any, it is finite, okay, it is finite members of tau, okay. Then OK is the finite members of tau, then their union of O k, where k is equal to, no, here we are not talking about union, here we are talking about intersection, okay, intersection, sorry, we are talking about intersection, yes. Then finite intersection of any yes, finite intersections of members of tau. So here k is equal to 1 to n must contained in tau. It's okay. And the third property is, the mathematically third property is phi. Phi means empty set, and the set itself should contained in or should belong to tau. So this is the mathematical definition of topology, okay. Now in order to understand topology, we must need some examples, just like I am taking over here. The first example is suppose the set X contains the element, just like X is the set, of course it should be non-empty, and this set contain the element just like A, and since the set contain the only one element which is A, and tau should be the collection, and in these two collections there are two elements. The first element is phi and the second element is X. So not I am taking X, here I will take A, okay. In collection tau these are two elements, okay. And if we check that either this is topology or not topology, of course it is topology, because when we take the union of phi and A, our answer is A, okay. Set A, and of course it tau contains set A, tau contains set A according to the first property, and the second property is when we take the intersection of phi and A, our answer is phi, and phi is of course exist in tau, and so the second property is also satisfied. And the third property is phi and X should be in tau. Yes, of course, phi means empty set, and this is X already exist in tau, okay. So all the properties are satisfied over here, so we can deliberately say that tau is a topology, tau is a topology on X, okay, topology on X. Okay, now I'm changing a little bit example. We'll take another example, just like I'm taking the example X is the non-empty set which contains two elements. The first element is A and the second element is B. Okay, and tau is the collection which contains the subsets of X. So what are the subsets of X over here? I am taking just like tau1, which is phi and X. Okay, in the first collection I'm taking phi and X, and tau2 is it is also just like phi and A and X. Okay, tau2, and now we take tau3, and in this collection we are taking phi and B okay. So phi, B and X, and there is another tau4. Tau4 is equal to we are taking phi A, and now we are taking B, okay, and X. So tau1, tau2 and tau3 and tau4, these are four topologies. Tau1 is topology, tau2 is topology, tau3 is topology, and tau4 is topology. For example, I'm just considering over here tau4. Okay, the first property is union of any members of tau should belong to tau. For example, if I take the union of A and B, okay, when we take the union of A and B, our answer is AB, and AB means that X and X exist in tau. And the second property is intersection. For example, if I take the intersection of any two members A and B, intersection of A and B, answer is empty set, and empty set exists in tau4. It means that this property also holds. And third property is phi and X should be in tau. Yes, phi and X are in tau, which means that tau4 is topology because axioms of topology are satisfied over here. In the similar way, we can check that tau3 is a topology, tau1 is a topology, and tau2 is a topology. Now we define the different terms just like which are used in topology. Here we are defining a little bit a different topology, a different space, and this space is called Sierpinski space. Sierpinski, yes. So what is Sierpinski space? The Sierpinski space is just like it is the Sierpinski space. It should be noted here that for any non-empty subset A of X, here we take the let A be the subset of X, A be the subset of X. Okay, if A is the subset of X, then the collection, and in the collections what it is, in the collections we are taking phi. Collection is just like it is phi, collection phi A and X. Okay, so our collection is phi A and X. Okay, when we take this collection, and this collection is must be a topology. Okay, we can write it just like as tau A. Tau A is equal to we are taking phi A and X. Remember that for we talk about for a non-empty subset, non-empty one subset, okay, and that subset is A. Over here we are taking, okay, So this is a non-empty subset. Okay, yes, the topological space, when we write it just like as X tau A. X tau A is the Sierpinski space. This is the Sierpinski space. Sierpinski this is the Sierpinski space. Okay, let me take another example, just like to understand the Sierpinski space. Remember that in Sierpinski space we take a non-empty subset. Okay, just like if I take the set X, and this set contain the elements just like A, B, C, D, E. A, B, C, D and E. Okay, these are the elements in set X, and I am taking tau 1 just like as tau 1 should be the subset of X. Here I am taking only one subset, just like phi and phi, and just like A, phi, A and X. Yes, so here is the subset of one subset of X is this. Okay, so this is a Sierpinski space. Remember that X comma tau 1, X comma tau 1 is a Sierpinski space. And now the question is, how many topology can be constructed on a non-empty set? It is unfortunately there is no method that how many topology can be constructed on a non-empty set. Okay, but in case of Sierpinski space, since it is defined on a non-empty subset of X, and the non-empty subsets of X, just like we know that if X has, just like if a set X has order of a set is just like 3, so it means that the total number of elements that can be created in X is 8. Okay, and since we take the non-empty subset of X for defining a Sierpinski space, okay, so it means that over here we can say that 2 raised to the power n. So 2 raised to the 3 is equal to 8, means that total number of 8 subsets can be created. But in case of Sierpinski space other than phi and X, 2 raised to the power n minus 2 Sierpinski topology can be constructed. Okay, because if a set has just like 3 elements, then the number of subsets that can be created for the set X is 8, which means that we can construct the 2 raised to the power n, 2 raised to the power n subsets. Okay, and the Sierpinski topologies can be constructed 2 raised to the power n minus 2. So here the question is, why the Sierpinski topology can be constructed in the number 2 raised to the power n minus 2? Because in the Sierpinski topology we take a phi and other than phi and X. Other than phi and X, how many subsets can be created? Of course, these are the subsets can be created other than phi and X. So these are the number of Sierpinski topologies can be constructed from a topological space from a non-empty subset X. Okay, hope you have understand about Sierpinski topology, and now we are taking another example to understand the topology. Okay, this example is just like I am taking X is equal to just like A, B and C. These are the elements. Okay, and we are taking the collection just like tau 1 is the collection, and in this collections our members are phi and A, phi A, C and AC and X. Tau 1 and the second is tau 2, and this is phi A, AB and AC. And X. And there is another tau 3, and tau 3 is another topology which is A, B, AB and X. A, another collection, not we are talking about another topology, this is another collection. Okay, tau 3 containing the collection A and B, also it is AB and X. Now we're taking tau 4, and in this collection our members are just like phi A, B and X. Phi A, B and X. Okay, here is tau 5, and in tau 5 we are taking just like it is phi A and B. Okay, and A, B. This is tau 5 and tau 6, and in this collection we are taking just like phi A, B, yes, phi A, B and AC. Yes, so these are the different collections. Here we are taking 6 different collections, and in these 6 different collections of subsets of X, we will check that which is topology and which is not topology. Here tau 1 and tau 2 are topology in X. Remember over here that tau 1 and tau 2 are both are topologies, because all the axioms of topology are satisfied. Union of any members of tau, just like if I take the union of A and C, so its union is AC, of course, exists in tau. And if I take the union of C and AC, our answer is AC, of course. The set AC, the subset AC exists in tau. And now we talk about the intersection, just like if I take the intersection of C and AC, our answer is C. Okay, our answer is just like intersection of A and AC. Okay, tau 1 is topology. I am saying over here that tau 1 is topology, intersection of A, C and yes, intersection. Here I am checking that tau 1 is topology or not. Yes, C and AC. Check over here, these are topology or not. What is the answer for yes, its answer should be I think that it's yes, answer should be C. Of course C exists over here. Okay, and if I take the intersection of A and C, our answer is empty, and empty is already exist over here. Also phi and x exist in tau 1, which means that tau 1 is topology. And now we check that tau 2 is topology or not topology. Of course, if I take the union of this and this, our answer should be AB, and AB exists over here. And if I take the union of AB and AC, our answer should be ABC, which means our answer should be X. ABC means that X, and X exists over here. And if I take the intersection of any two, just like I'm taking the intersection of AB and AC, our answer is A, and A exists in tau 2. Also phi and X exist in tau 2, which means that tau 2 is a topology because all the axioms are satisfying over here. And similarly, tau 3 is not a topology because it does not contain phi. Here you see that phi does not exist over here in this collection. Since phi does not exist over here, so tau 3 is not a topology. And tau 4 is not a topology on X also. Why? Okay, because union of A and B is AB, and AB does not exist in this collection tau 4. Okay, in this collection AB does not exist. If I take the union of A and B, our answer is AB. The set AB, the subset AB, and the subset AB does not exist in tau 4. And similarly, so tau 4 not is the topology. And similarly, when we talk about tau 5 is also not a topology on X because it does not contain X. Remember over here that in tau 5 there is no X. So phi, and the third axiom is phi and X must be in the collection. So phi and X does not exist in this collection. Therefore, tau phi is not a topology. Now it is tau 6. Okay, either tau 6 is a topology or not topology. Okay, we'll check that. If we take the union of AB and AC, our answer is AB. Yes, of course. So X does not exist in tau 6. X does not exist in tau 6, which means that tau 6 is also not a topology. So these are the different examples to illustrate the topology. Okay, now we will move a step ahead, and these steps are just like we are now defining in discrete topology. So what is, after defining the topology, what is in discrete topology? In discrete topology, okay, the collection of the empty set and the set X itself is a topology on X. The collection of empty set empty set phi and the set X and the set X is, yes, that X itself is a topology on X, is a topology on X. Okay, so this collection, in this collection, in discrete topology, our collection is only phi and X. So the topology on phi and X is called the indiscrete topology. Okay, Yes, in other words, for any non-empty set, just like X, the collection, what type of collection? The collection contain, it is phi and X. Yes, this collection, and this collection is an in discrete topology on X, and the space X comma T, here we write X comma, this space is in discrete topology, in discrete topology. Okay, so now we are taking some examples to determine whether or not each of the following collection of subset of X is a topology. Okay, here I am taking some more examples, just like in these examples, the first example is just like it is these example also illustrate about topology. X is the set which contains the element A, B, C, D and E. These are the elements of set X, and here I am taking different collections, just like tau1 is the collection which contains the element phi, A, B and yes, AB. AB and AC, tau1, and we are taking another collection which is tau2, and in this collection we are taking phi and A, C, phi, A, C comma D. Okay, yes, C comma D. Okay, and then we will take just like it is A comma C comma D. Okay, then B, C, D, E, B comma C comma D comma E. Okay, and this is X. Yes, this is tau2, and here we are taking another topology, just like it is tau3 topology. We are taking, these are collection, not topology, and we will check that either these are topology or not topology, and if these are not topology, then what is the reasons these are not topology. Okay, and here just like tau3 which is equal to phi and A, B, C, A comma B comma C, then A comma B comma D. Okay, A, B, C, D, A comma B comma C comma D, and of course it is X. So these are the collection, tau1, tau2 and tau3s are collection, and now we check that either these collections are topology or not topology. Here tau1 is not a topology on X because AB and AC, yes, AB and AC belong to tau. When we take the union of AB and AC, our answer is ABC, and A, B, C does not exist in this collection. Okay, yes, in this collection A, B, C does not exist, so tau 1 is not a topology. Tau 2 is a topology because all the axioms, 3 axioms, are satisfied over here. When we take the union, you will find the answer in tau 2. When you will take the intersection, you will find the answer in tau 2. Okay, so what is about tau 3? Tau 3 is not a topology. Why? Because when we take the intersection of A, B, C and A, B, D, A, B, C and A, B, D, when you will take the intersection, and you will find that your answer is A, B. So in this collection there is no A, B subset of X. Therefore tau 3 is not a topology. Okay, hope you have understand that what we have defined over here, and how to illustrate the topology with examples. And I am fully I can say that this lecture is very useful for you, because I have described these examples, and examples are of course are helpful to understand the concept. Thank you very much, and I will meet you in the next lecture.